In this video, we shall discuss about a problem. You have to show that this set of vectors is an orthogonal basis for the Euclidean space R3 with the standard inner product. And you have also to express this vector 4, 3, 2 as a linear combination of these vectors. R3 is a vector space having dimension 3, and this set of vectors having 3 vectors. So if we can show that this collection is indeed an orthogonal collection of vectors, if we can show that this collection of vectors is indeed an orthogonal collection, then obviously these vectors will be linearly independent. That means this is a set of 3 linearly independent vectors, and R3 being a vector space having dimension 3, of course this would be a basis for this R3 vector space. So first and foremost, let us try to show that this collection of vectors is an orthogonal collection. We have renamed here. This vector 1, 2, 2 we have considered as alpha 1 vector. The second vector 2, minus 2, 1, 2, minus 2, 1 we have considered as alpha 2 vector, and the third vector 2, 1, minus 2 we have considered as alpha 3 vector. So let us now calculate the inner product value of these 3: alpha 1, alpha 2, alpha 1, alpha 3, and alpha 2, alpha 3. First one, alpha 1, alpha 2. The first component of this alpha 1 vector is 1, and the first component of this alpha 2 vector is 2. So we have written 1 into 2. The second component of this alpha 1 vector is 2, and the second component of this alpha 2 vector is minus 2. So we have written 2 into minus 2. And the third component of this alpha 1 vector is 2, and the third component of this alpha 2 vector is 1. So we have written here 2 into 1. After calculation we have this is equal to 0. Similarly, we have calculated alpha 1, alpha 3 vector inner product value of this ordered pair. The first component of this alpha 1 vector is 1, and the first component of this alpha 3 vector is 2. So we have written 1 into 2. The second component of this alpha 1 vector is 2, and the second component of this alpha 3 vector is 1. So we have written here 2 into 1. The third component of this alpha 1 vector is 2, and the third component of this alpha 3 vector is minus 2. So we have written here 2 into minus 2. After calculation we have this is equal to 0. Similarly, we have calculated alpha 2, alpha 3. The first component of this alpha 2 vector is 2, and the first component of this alpha 3 vector is 2. So we have written here 2 into 2. And the second component of this alpha 2 vector is minus 2, and the second component of this alpha 3 vector is 1. So we have written here minus 2 into 1. The third component of this alpha 2 vector is 1, and the third component of this alpha 3 vector is minus 2. So we have written here 1 into minus 2. After calculation we have the value of alpha 2, alpha 3 equal to 0. So each of these alpha 1, alpha 2 is equal to 0, alpha 1, alpha 3 is equal to 0, and alpha 2, alpha 3 this is also equal to 0. So the collection of vectors, these alpha 1, alpha 2, alpha 3, that means this collection of vectors is indeed a orthogonal collection. So this collection of vectors is also linearly independent, and these being three vectors 1 2 3, the set, this set having three linearly independent vectors, and R3 being a vector space of dimension 3, this set would be a basis for this vector space R3. So any vector from this vector space we can write as a linear combination of these vectors. Now try to remember, or let us recapitulate the previous class, the theorem which we already learned in our previous class. That was, for any orthogonal collection of vectors, if we consider the linear span of that very collection, any vector from that very collection can be written as a linear combination of the vectors forming the orthogonal collections, and these scalar components are basically the components of this vector alpha along the corresponding vectors. Okay, so here this 432 being a vector from this vector space R3 and this collection being a basis of R3, we can write this vector as a linear combination of these vectors in such a way. If we rename this 432 vector as alpha vector, then alpha vector equal to C1 into alpha 1 vector plus C2 into alpha 2 vector plus C3 into alpha 3 vector, where each Ci is a scalar component of this alpha vector along alpha I varies from 1 to 3. So how to calculate these scalar components? Try to remember that this is, if the scalar if C be the scalar component of alpha along the vector beta, then we can use this formula C equal to alpha comma beta by beta comma beta. We are C is the scalar component of alpha along the vector beta, so C equal to alpha comma beta divided by beta comma beta. We are using this formula here. C1 is the scalar component of alpha along the vector alpha 1. So C1 equal to alpha comma alpha 1 divided by alpha 1 comma alpha 1, and we have calculated this alpha comma alpha 1. Alpha is 432 and alpha 1 is this 1 to 2. So we have calculated this, and this is this, and similarly alpha 1 comma alpha 1, that means the square of each and every, the summation of the square of each component of this vector alpha 1, and we have calculated this, and the calculated value is equal to 14 by 9. Similarly, we have calculated C2 being the scalar component of alpha along the vector alpha 2. We have written here alpha comma alpha 2 divided by alpha 2 comma alpha 2, and we have calculated this portion here. We have calculated. Similarly, C3 being the scalar component of the vector alpha along the vector alpha 3, we have written C3 as alpha comma alpha 3 divided by alpha 3 comma alpha 3, and we have calculated these as we have done in our previous cases, and this the value is this. So alpha equal to C1 alpha 1, C2 alpha 2 plus C3 alpha 3. In place of C1, C2 and C3 we have these values. So alpha vector equal to this into alpha 1, this into alpha 2 plus this into alpha 3. Okay.